Hello, my name is Anastasiya Kochkina, and today I'll walk you through our work on improving model explainability in dynamic facial expression recognition for hybrid intellectual systems. So we will start with introduction. Facial expression recognition has made big strides, but doing it in the wild with changing light, head pose, and occlusion remains tough. Classic CNNs do well on single images, yet lose spatial context when the face moves in 3D. We restore that context by treating each face as a graph of landmarks. Then we follow that graph through time with transformer encoders borrowed from NLP. The result is our spatiotemporal graph transformer, or STGT. It matches state-of-art accuracy and comes with a built-in explainability hooks that show which landmarks and which frames drive every prediction, critical in healthcare, security, and personal data settings. Finally, because conversation is multimodal, we plug STGT into Llama-based text-to-speech engine, so the system can see, explain, and respond with human-level nuance. So we will start from introduction, then dive into our objectives, data architecture, and results. Research objectives. 4 concrete goals guided the study. Build the architecture that fuses graph proceeding with transformer self-attention to create STGT. Embed explainability by integrating attention attribution, future ablation, gradcam, and attention rollout without hurting accuracy. Deliver granular explanation that surface landmark and frame level evidence for every decision. Achieve full multimodality by chaining STGT to speech-to-text, a dialogue manager, and LASA TTS, so conversational agents respond with the right words and the right tone. Talking about dataset and preprocessing. Our experiments rely on the Naumov video corpus. For receiving facial landmarks, we chose MediaPipe framework because of its resistance to light changing and interferences. MediaPipe face mesh usually extracts 468 3D points per frame. We prune 268 key landmarks to lighten the transformer load. Clips are bucketed into 3 sequence lengths: less than 50, less than 100, and less than 150 frames, giving us totally 7,700 labeled videos after cleaning. Data structure. Each sample is stored as a tensor of shape T multiple N multiple 3 plus a class label, making batches easy to stream directly into the model. 3 means dimension, so it's x0, y0, z0 for 0.1. And 667, y67, and z67 for 0.68. This tidy, balanced dataset is ready for training. Talking about model architecture, let's unpack the STGT stack in more detail. So, the landmark embedding layer, every row XY, that triplet is linearly projected into D-dimensional space. Optional positional encodings mark landmark identity. Spatial transformer block within each frame, multi-head self-attention, lets landmark attend to one another, modeling muscles that move together. Layer norm and a feed-forward network refine the signal. Temporal transformer block with flattened spatial info so that each time step becomes a token. Stacked encoder layers attend across frames, capturing motion patterns like the arc of a smile. Gradient hooks here power both spatial and temporal gradcam. Global average pooling condenses the T-length sequence into one vector, ensuring permutation invariance over time. Classification head, a fully connected layer, outputs logits over the 11 emotional classes. This architecture captures where an expression happens, how long it lasts, and thanks to the hooks, why the network is confident. Now we approach Tuxai implementation. Accuracy means nothing if it's a black box, so we wired 4 explainability tools straight into training. Attention attribution. We grab raw attention weights from both spatial and temporal blocks and then turn them into landmark and frame heatmaps. Feature ablation. Knock out landmark groups and watch the accuracy drop to rank importances. GradCam and temporal GradCam, gradient-based saliency adapted to a transformer backbone, visualized frame by frame. Layer-wise relevance propagation. Backpropagate relevance scores all the way to each landmark in each frame. Together, they are triangulate while the models say anger or joy. On this slide, you could see how tension and tension was calculated for this model to increase explainability. So on the top, it shows how spatial GradCam has been calculated, and for temporal GradCam, this process is extended over time by computing gradients across sequential frames. Also, we would like to show you results we received from GradCam, and we have some frames across videos where the man is supposed to be happy. The low attention intensity shows as blue, and this is frame 9. So we can see here the areas are totally blue, and once he starts to smile, his corners of lips becomes orange, green, and brows becomes yellow. So medium attention intensity shows as green to yellow. The frame 12, the target class is the same, and high attention intensity shows as orange to red. So we can see on his eyes, on his lips, on his brows, that model understands where to put her intention. As an outgoing project, we will integrate our model into a hybrid intellectual system, and I would like to speak with you about its end-to-end pipeline. For perception front-end, SDGT analyzes the face at 20 times per second, and speech-to-text ASR transformer pipes in the live transcript to get not only what's been said, but also how. The collected data will be put through the dialogue reasoning layer, which stores the latest emotional label and prompts a language model for empathic wording. Sad triggers gentle reassurance. Angry triggers calm, solution-focused language. Response generation. Text plus emotion tag flow to Lhasa TTS, producing synchronized expressive speech. Following up, we keep going with emotion adaptive speech with Lhasa. Lhasa maps semantics and emotion to process the pitch, rate, and pause. Under the hood, a llama text transformer chooses words. A VQ codec renders expressive waveforms. Process reward model tweak articulation until voice and detected affect align. We keep on 2-person dialogue videos and keep a human in the loop so the bot responds to your feeling, not just with it. As a part of discussions, there are 3 key takeaway highlights from this research. STGT is the sweet spot. Graph plus transformer design delivers high dynamic facial expression recognition accuracy and landmark level transparency via GradCam, attention attribution, and feature ablation. Explainability matters. Pinpointing which landmarks and frames drive a prediction builds trust for healthcare, security, and HCI use cases. Rosebud 2 in the wild noise. Attention maps help the model adapt to lighting, occlusion, and head pose changes. What's next? Multi-phase tracking. Benchmark YOLO phase and media pipe will be compared between each other and explore a hybrid detector for tougher scenes, especially when we use multiple phases. New backbones test sparse attention low rank variants for lighter, faster inference. Temporal explainability. Extend GradCom to the time axis, roll out token level Xi on the language side. Unified perception to dialogue to speech loop. Weld STGT plus ASR into a single stream, feeding the dialogue manager and LASA TTS for real-time emotion synchronizes replies. Bigger, fairer data. Train our models on long-term multimodal corpora to learn emotion flows across turns and reduce demographic bias. Edge readiness. Investigate lightweight transformers and efficient attention to cut latency without sacrificing accuracy. Thank you for your attention. Now please feel free to ask me your questions.